This lab is on the ground and excited state ionization constants of 2-naphthol. I recommend that you watch the PowerPoint on this lab before working on it, whether you do it in person or online. Hi, so today we'll be doing the 2-naphthol lab. There are 5 solutions that have to be prepared in this lab. Solution 1 and solution 2 are the acid and base forms of 2-naphthol. So in the acid form we have added sulfuric acid that makes sure that that OH in the 2-naphthol is always protonated. The second solution is the base form where sodium hydroxide is added that deprotonates that 2-naphthol, so it is the 2-naphthoxide ion. So those two solutions have the same concentration of 2-naphthol, but one is in the acid form and one is in the base form. Then we have solutions A, B, and C. All right, and A, B, and C have different amounts of the weak base ammonia and the conjugate acid ammonium chloride. So the ammonia and the ammonium chloride solutions are both 1 molar, but we have varying amounts of those two solutions in those in the 3 volumetric flasks that are A, B, and C. They all have the same amount of the 2-naphthol, but they have varying amounts of this weak acid and weak base. So they have 3 different pHs. So we will measure the pH of those 3 flasks, and then we'll take all 5 of those solutions, 1 and 2, and A, B, and C, and take the UVVis absorption spectra of those 5 samples. From those spectra, we will be able to figure out what the concentration of the 2-naphthol and the 2-naphthoxide are in the 3 solutions A, B, and C. So whereas in solution 1 and solution 2, we have only all acid or all base, when we have these pHs of this experiment for A, B, and C, which are in the 8 to 9 range, there's actually different amounts of the 2-naphthol and 2-naphthoxide species. Okay, and knowing those concentrations and then measuring the pH of those solutions, which gives us the H3O plus concentration, we will be able to figure out 3 different determinations of the Ka. And that sound you hear in the background that sounds like an occasional waterfall is the pipette washer that I happen to be trying to accomplish 2 things at once while I film this lab and run the pipette washer, and it is July 31st. Okay, so I just wanted to show you what we have here. We're going to have solutions 1 and 2 over here, and they both have the same amount of the the same amount of the 2-naphthol, 20 mils of the stock solution, and then 20 mils of acid. And over here for solution 2, we have 20 mils again of that 2-naphthol, but now we have base instead of the acid. And then over here we have the 3 solutions A, B, and C, and like I said, they have the same amount. They all have 20 milliliters of the 2-naphthol, but A has 10 mils each of the same concentration, 1 molar, ammonia and ammonium chloride. B has 20 of the ammonia, 10 of the ammonium chloride, and C has 10 of the ammonia and 20 of the ammonium chloride. And since ammonia is a base and ammonium chloride is an acid, you should be able to figure out which of these has the higher pH and which has the lowest pH. And you'll be measuring those pHs in the lab. Hi. So it would be kind of silly for me to show you how to prepare all these solutions, but in the interest of I don't know, just showing you that I'm actually doing this thing for real, I'll show you a little bit of pipetting until it gets a little boring. So here I am pipetting 20 milliliters of the 2-naphthol solution into the first volumetric flask, and I'm going to put the same amount, this 20 mils of 2-naphthol, in each of the other volumetric flasks, and then I will continue with the other solutions. Okay, so I just got through pipetting 20 milliliters of the 2-naphthol into each of these 5 solutions. You can see there's quite a bit of liquid in there. And now I'm going to add the sulfuric acid to 1, the sodium hydroxide to 2, and then the varying amounts of ammonia and ammonium chloride to A, B, and C. So what I did was I put the H2SO4, the NaOH into 1 and 2, and then I put the ammonia and the ammonium chloride into A, B, and C. I filled it almost all the way up to the mark. But now I'm going to fill it up to the mark, each one, and then invert and mix 10 times. So that's the next thing I'm going to do. And, it was a little sloppy, but I think I did it. Nope, I think I need a couple more drops. Good. All right, so you've seen this before. This is no need for me to show you this 5 times. You've done it all yourselves. I have to admit, I don't do this very often anymore, so having to do it this summer, it's a good refresher course. Okay, so now I have my solutions A, B, and C, and I'm about to measure their pHs. Okay, so I put a portion of each solution in these 3 cups, and now I'm going to get ready to measure the pH. The pH probe is sitting in a pH 10 buffer solution, which is reading pretty close. I calibrated this just now. So hang on and we'll measure those pHs. All right, so I've rinsed off the probe, and now I'm going to take my first solution, which is solution A. Let's dip it in. Okay, and I'm going to mix it around just a little. There you go. Hold on a minute. Looks like it's 7, sorry, it's 9.356 for solution A. Okay, now I'm looking at solution B. Okay, so I'm going to give it a little mix. Wait till the reading stabilizes. Usually we get a beep when it's stabilized. .648. Okay, I'm going to again stir this a bit, wait for the reading to stabilize. Push this in a little further. Good. I'm going to wait for the beep. Hope I get a beep. All right, 9.224. Okay, so you could see these are my numbers for solution A, B, and C. Solution A, which has the same amount of the ammonia, and the ammonium chloride is about 9.34. And then in the next solution, where I've got more ammonia, which is the basic element or compound in the solution, and it's gotten a little more basic. Right now, in this one, where I've got more of the ammonium chloride, which is acidic, pH is down a bit from the 9.356, okay? So these numbers make sense. So what we're going to do next is take another portion of solutions A, B, and C, as well as our solutions 1 and 2 that we still have here, and I'm going to take the UVVis spectrum. So first I'm going to fill my 5 cells. I've got 5 cells ready and waiting here, okay? And actually I've got 6 because 1 is going to be the reference. And I'm going to fill them all with distilled water, and the next time I see you I'll be over by the UVVis and starting to go about taking those spectra. So here I am at the UVVis instrument, and I'm going to turn on the computer. Hopefully it's already on. Let's see. Right. Let's see what I'm going to do here. Carry Win UV. Open up the workstation. And I'm going to do a scan. Okay. And now I have to pick my parameters. So let me check my sheet here. And let's see. Okay, so according to the instructions, I should fill my cells like this. I should put my reference over to the left, and then fill them from left to right, 1, 2, ABC. But all I have in these cells right now is distilled water. I put distilled water in them, labeled them, because I'm going to put the samples in afterwards. So I'm going to put the reference right here in the first compartment, and then I'm going to fill 1, like it says, 1 on the left, on the right, and then 2. I already wiped these with Kim wipes, otherwise I'd be doing that furiously right now. A, B, and C. Because what I'm going to do is run a baseline. But I have to get the wavelengths in here. Let's see. Alright, so once I have my samples in place, which I do, I'm going to be selecting this icon here. This is actually the method icon. And I guess I'm already there. And I'm going to take my scan from 400 nanometers to 250. Okay. Then I'm going to set this averaging time here 2.5. Let's see if I can get there. Which makes it 120 nanometers per minute as a scan rate, which is what I want. Okay. Then I choose this icon, and I can tell the instrument how many samples I have, and I have 5 samples. Right, so over here, instead of 7, which is the maximum I could do, I just change this to 5. And I tell the instrument that I want to run a baseline. So what that means is it's going to run my empty cells against the reference, and any differences will be accounted for when I pour out the distilled water and put in my samples 1, 2, A, B, and C. I'm also going to set my temperature to be 25 degrees C, but first I actually have to go over here and well, actually I have to turn the instrument on. There's an on-off switch. Turn that on or this won't work. So I see that this little icon up here, this thing here, is separated. So if I do this, this is what I have to do, is click on this thing here. And it doesn't work. Actually, it did work, and now it looks like this thing here. Notice that it's connected and it's green. Okay. It didn't work before, but then I did a million updates on the computer, so now it's working fine. So you can see I'm scanning from 400 to 200. I think it should be 250. Okay, let's fix that. And I have a scan rate of 120 here, which I got by choosing 0.5 as the averaging time. I told it that I have 5 samples and that I wanted to do a baseline correction. And the other thing I'm going to do is go back to the method, and I'm going to ask the instrument to keep this at 25 degrees C. Apply that temperature so you can see. What's going on here is we have the black numbers and the red numbers. The red number is what the temperature is set to, and the black number is where it is. So I believe that once the temperature comes down to 25, we'll be able to run the spectrum. Or take the baseline. That's what we have to do first. So I'm going to hit this arrow, and I am prompted to give a file name. So I'm going to choose LC for my initials, and I'm going to go to Naphthol to N. Oops. I don't know why it's not capital. So after giving it a file name, it accepted it eventually, and then I get this, and I hit OK, because it's going to run the baseline. These are all baseline samples. Say OK. It's making a lot of noise. Okay, so you could see all these basically lines doing nothing. Now, it's very funny. I have one cell that's a little bit lower than the others, so it's kind of odd. But honestly, if I keep the same cells in the same position, the baseline correction should take care of that. It's going kind of slow because I put it at a nice slow scan speed. So I'm going to have to be very careful to keep the cells in the same positions after I put the solutions in them. I'm not liking what that blue one is doing because it looks like it maybe has something in there. It's giving a reading. Okay, so I've decided not to do anything about this sample here, which looks a little off over here, because where I'm going to actually be measuring is at 345 nanometers, which is over here, and everything looks okay over there. So the next thing I have to do is put the samples in and then hit OK. Okay, so I've just replaced the distilled water from 1, 2, A, B, and C, those solutions, with the actual solutions, and of course left the reference distilled water alone. Now I'm going to go back here, and I'm going to click OK to run these samples all at once. You can see all the samples are doing something slightly different. I'm loving that I got that nice crossing point there. Means I did a pretty good job on those solutions for someone who doesn't do that too often. Nice. All right. So now I can take my cursor. I think I have to measure at 345. If I just hold the cursor there at 345 nanometers, I can get a little table here that tells me what each of the samples did. Well, first it gives me the 4 baselines, and then it gives me the samples. Sample 1, 2, 3, 4, and 5, which is 1, 2, A, B, and C. Okay, so I'm going to make a copy of that. So here are the spectra of solutions 1 and 2, and then A, B, and C. I'll show you another one where they're properly labeled. But what I just wanted to point out here is that on the right, there's a table that has the absorbances of all of those samples at 345 nanometers. And this spectrum just sort of blows it up a little bit so you could see the entire spectrum of each one of the samples, but it doesn't have the wavelengths next to it. That'll be on the next slide. And here's that nice table. So it's really 1, 2, A, B, and C that we're interested in, and gives the absorbance values of those 5 samples. And then this last slide just shows a blow up of the relevant part of the absorption spectrum for solutions 1, 2, A, B, and C, and then it also gives the absorbances as well. So we're basically up to the last part of this lab. And what remains is we have to find the transition energies, the delta E's between the ground and excited state for the NOH as well as the NO- form. And we need to use these delta E's in what's known as the Forster cycle method that's talked about in the lab handout and also in the PowerPoint on the lab. At the end of that PowerPoint, it's concluded that the delta E for each of those species, the acid form NOH and the base form NO-, this is the energy difference between the ground and the excited state, which I talk about how it's really the 0-0 transition energy, may be obtained from the crossing point of an absorption spectrum and an emission spectrum of each of those. So we use solution 1, which is the NOH form, and we find that crossing point, and then we use solution 2, and we find its crossing point. But it turns out that in this lab, we actually do not take a separate absorption and emission spectrum of each of these and find the crossing point. We do something a little bit different, which is using something called a fluorescence excitation spectrum, which I don't think you've ever heard of. So what I'm going to do is explain it a little bit before we do this part of the lab. Okay, so what we could do in order to get this crossing point, as I've said, is we could get an absorption spectrum and an emission spectrum, and then find this lovely crossing point right here. Okay, but we're actually not going to do that because that would require using 2 separate instruments. And it turns out that we don't have to do that, that we can get both of these spectra from a single instrument. Okay, so first of all, I'd like to tell you about emission spectra because I'm not sure I have ever actually done that. I don't think so with this group. I know I haven't. So what you do when you take an emission spectrum is you excite at a single wavelength. So in this case, it would be at 327 nanometers. And then you detect emission as you vary, as you sort of scan through these wavelengths here where the sample emits. And you do that by changing the monochrome is a monochromator, which is something that selects different wavelengths. And you simply vary that as you collect light that's coming out of the sample in fluorescence. And it gives you a profile of the intensity of the emission, just how many photons are coming out per second sort of thing. Okay, so I said there's an easier way than using an absorption instrument and a separate emission instrument, and that is that instead of taking an absorption spectrum for this spectrum on the left here, I would take something called a fluorescence excitation spectrum. And we do that using the fluorimeter. The fluorimeter is the fluorescence instrument. And so what we do is we set the detector to one wavelength, which for the acid form of 2-naphthol would be 354 nanometers. Okay, that's what I'm showing you here, nanometers. So that means that our detector is only open to light at 354 nanometers, and it will detect the intensity of that light. So then what we do is we vary the excitation wavelengths over the whole range of where the 2-naphthol absorbs. Actually, we're only interested in that band that's around 330 nanometers. So we will go like, we'll start at 300 and we go, and most of the absorption happens here with a lot of it happening around 327. Okay, so we scan through those wavelengths. Now, what actually we are able to do then is, as we start the scan, so we're starting off at a very, maybe 300 nanometers, and the detector sees nothing. So your intensity will be basically nothing because the sample needs to absorb light in order to emit light. Over here, it absorbs nothing, so you see no emission coming out. Okay, so at that wavelength, you see nothing. As you increase, as you go through this absorption spectrum, and now you're scanning at wavelengths that are going up and up to the 327 maximum, you're going to see more and more light coming out. Okay, so even though you're only looking at light at 354, as you scan through these wavelengths, you are getting more and more emission intensity as you scan through these wavelengths where the sample absorbs, until finally you get up to 327, and now that's the wavelength of maximum absorbance. So guess what? It's going to emit the most light, and you will see a maximum there. And then as you come down on the other side of this curve, there will be less and less emission. So this is an instrument that measures emission intensity, but it does it by varying excitation wavelengths and looking at the emission intensity as a function of excitation wavelengths. And what it ends up giving you is something that has the same profile as what the absorption spectrum would be. And there's another wonderful added benefit of this. I've said that when you measure this crossing point, you need to have the heights of these two spectra, absorption and emission, or excitation and emission. They have to be the same. Otherwise, it'll affect where this crossing point is. It'll move it to the right or left. If I were to have this intensity here much higher, then the crossing point would be like further that way. Okay, so that's why you have to have them the same height. Well, when you do it with the fluorescence instrument, both this height and this height correspond to exactly the same thing. Exciting at 327 and watching emission at 354. Let me explain. When you take an emission scan, you excite at 327, the wavelength of maximum absorption, and you scan through the emission wavelengths. So when you get up to 354, you're exciting at 327, and you're watching light come to the detector at 354, and that has a particular intensity. Okay, when you do the excitation spectrum, you're opening your detector at 354, but you scan through the excitation wavelengths, and guess what? When you get to 327, you're exciting at 327, you're watching at 354. For both spectra, the maximum heights are for exciting at 327, emission at 354. So So when you do it this way, you don't have to worry about that. And when you do solution 2, then we're exciting at 340 nanometers, and the emission is 419, but it's the same idea. It's just a little bit shifted over this way, right? So it's a little bit, shifted in this direction, wavelength shift for the base form. So that's that. There is yet one more part of this experiment to do, and it involves fluorescence. So here's the fluorimeter, and this is where our samples go in the fluorimeter. There's a single sample compartment right there. Okay. And we're going to click on the carry eclipse icon, which is one of the many icons on this instrument. So there it is, carry eclipse. Okay, and then I'm going to set the parameters. I'll come back. So as soon as I clicked on that carry eclipse icon, I have this whole range of things to choose from. So I'll pick the scan icon, and that opens up the software. Okay. So I'm going to set this experiment up. And then I get the setup menu right here. All right, so what I'm going to do is I'm going to do these solutions one at a time. I'm going to first take solution 1 and place it in the sample compartment right here. Okay. And then what I'm going to do is set up to do a fluorescence emission spectrum and a fluorescence excitation spectrum. So solution 1, if you remember, is the acid form of the 2 naphthol. And according to the directions for solution 1, for the excitation scan, I'm going to set the emission wavelength. Let's see, excitation scan. Emission is going to be 354. And then I'm going to start, I believe, at 300 and go to 500. Okay. And let's see what that looks like. I wonder if the instrument's not turned on. Is it turned on or? No, it's not turned on. That's why this green light's not going to go on. I'm going to wait for the green light. There's the green light. Now I'm going to hit the start. See what it looks like. Oh, I'm going to call it sample 1 because it is solution 1, so that's not a bad name. All right, so here's my spectrum. Okay. It's off scale here. All right, so to bring everything on scale, I'm going to have to change something in the setup menu. Oh, I know, maybe the slits are too big. Let's see. What do the directions tell me about the slits? Oh, 5 and 2.5. I'm letting too much light in. 5, and I'm going to change this to 2.5. Oops. Okay. And then it wants me to go to manual here. Go into options and change that to 640. Let's see if that works. We want it to be, we want the maximum to be near 1,000, but not over 1,000. And here we are over here. Okay, so 600, it's not that, I'd like it to be a little more than that. I might change that voltage. What I was doing was I was adjusting the voltage on the photomultiplier too. I'm going to set it to 660. Okay, I'm going to run it again. All right, I like that better. Maximum is around 850 or so. I'm going to get rid of these two. Remove graph, and I'm going to get rid of this one. Oh, well, now I have this little, you know what, I'm going to remove this one as well. And I'm going to start from the beginning because now I know what everything should be set to. And so I'm just going to do setup. It's already set up. And now I'm going to just do this. And it's going to call it, let's call it sample 1 because it is solution 1. Now I have a nice on-scale excitation spectrum of my 2 Naphthol. All right. When it's done, I'm going to set up the emission scan. Okay, so I'm going to go back to setup. Instead of excitation, I'm going to do emission. This is going to be, I believe, 327. Turn. And now let's go and do that one. I'm going to call that sample, I'm going to call it 1B. Okay. Alright, so that's the emission spectrum. Now what I'm going to do is save these files as CSV files, and I'm going to open them up in Excel and put both of them in the same graph, and I'm going to find the crossing point of these 2 graphs, and that's going to be my wavelength that I'm going to use for the excited state Ka calculation. Okay, so that's okay, so now I've placed sample 2 in the compartment, and I'm going to do an excitation spectrum of sample 2, and according to the directions, this wavelength should be changed to 419 nanometers. Return. And I'm going to call it sample 2 for solution 2. Okay. But I'm a bit off scale here, so I'm going to have to adjust that photomultiplier voltage. So I have to go back to the setup menu as soon as it's done. So I'm going to change this voltage here in options to maybe 640. Okay. And I'm going to delete this graph because it's just not helping me any. I'll better leave these. Okay, so now I'm going to start with the corrected. I'm going to call this sample 2 again for solution 2. And it's now on scale, which is what I wanted. Okay. So that's the excitation spectrum. I'm going back to the setup menu. Oh, it's not done yet. Oh, now it's done. I'm going to go to emission. And I have to change that wavelength to 340. And now I'm going to run it. I'm going to call it sample 2B. It's over there. Right there. Okay. All right, and now what I'm going to do is file. Save method as. So I'm going to choose to save it as a spreadsheet ASCII file. And I'm going to call it, let me lock the caps, LC to Naphthol solutions 1 and 2, 7, 31, 20. Okay. All right, so here's the Excel spreadsheet that has the data for solution 1 and solution 2. The first 4 columns for solution 1, and the next 4 columns are for solution 2. And what I'm going to do is, since these wavelengths are all the same, I'm going to delete the columns that have the wavelength in them. I'm just going to use the first column. Okay, and now I'm going to ask it to, I think I did that wrong. Gotta Control Z that. I think I got rid of the wrong one. Okay. Oops. Okay, so I messed around with my columns a little. And I have the wavelength there in the first column A, and the 2 intensities, sample 1, the excitation and the emission, and then I copied the wavelengths again, and now I have solution 2, the same thing. These labels are really not right. This is sample 2, and this is sample 1. Okay, so now I'm going to plot this, and this will give me this will give me what the acid form looks like, the spectra. I'm going to do insert, scatter, but I'm going to have it just be the lines. Okay, look at that. So I just got to mess around with the scale a little bit. In fact, I'm going to move the chart to its own sheet. Okay, I'll deal with the scale on that. And now I'll go back to this, and I'll plot the other solution 2 as well. Insert, scatter, connecting lines. Okay. Okay, so when you go to write up your own lab for this, I'll give you an Excel spreadsheet with the wavelengths and the excitation and emission spectra data, and you'll choose an appropriate scale for the 2 sets of spectra. You'll have 1 page for the solution 1 and 1 page for solution 2. You'll label the axes and put a title, and then you can actually find the crossing point using Excel by running your cursor on that crossing point, and it will give you the coordinates of that point. If you take your cursor, you could find the closest data point. It says it's 300 and 75 or so nanometers where it crosses. When you do this, you should label your wavelengths here, and this is just fluorescence intensity on the y-axis. So that's the base form right there.
So I just want to make sure that you know that you'll be getting an Excel spreadsheet with wavelengths and those emission intensities for both the excitation and the emission spectra, for both NOH, which would be from solution 1, and NO minus from solution 2. And you need to use this data to make proper graphs with a good scale to find those crossing points, those wavelengths where the spectra cross for these two species. Make sure you have a good descriptive title on the graphs and have properly labeled axes. And you should indicate what the values of the crossing points are for each, for NOH and for NO minus, right there on the graph.